What about buckling of a tube? Well, how can the tube buckle? I believe that one of the favorite beverages in this generation is soda, right? You must have the experience of smashing an empty soda can, the aluminum can. I don't know, in high school. You don't do that in college anymore, right? Because you're adults. So that kind of behavior is what we call buckling. Imagine that you have an empty soda can, and when you smash it, you realize that you don't have to provide too much force, especially if you just pinch in the sidewall of the can a little bit, that you can break it very easily. That kind of behavior is what we call the buckling of a tubular structure. So in that case, the loading is uniformly distributed like this. And of course, you also have simply support. Like this. When it buckles, it actually looks like this. First, it's going to exhibit some horizontal behavior, deflection. There's always this part in reality. The structure is going to deform anyway. But after reaching the critical load, PCR, you would jump to another point, which corresponds to a much lower force. And this jump is what we call snap-through buckling. So this will happen very, very fast. It will go like this. And actually, I should use a different curve to describe it. I should use different color. And come back to here. So imagine you draw the vertical line like this. And the loading curve is going to go down like this to some point and will catch up from there. Goes like this. In other words, for tubular structures, when it buckles, you know, that's how you actually will enjoy the fun when you try to smash an empty soda can, because the loading level will drop all of a sudden from a very high level to a very low level and start taking additional force after the buckling. So this is the conceptual curve for the buckling of a tube. The next one. Buckling of an arch. Now, we have seen that columns can buckle, tubes can buckle. What about an arch? Of course, arches can buckle from the some of the photos I showed you before. Suppose we have an arch like this. This could be a parabolic arch or a spherical arch or circular arch, any kind of arch you want to consider. Actually, let's draw this a little bit thicker, like this.
On the tube, you called that snapping?
Yes.
Buckling? Okay.
Yeah. And so later on, we will talk about the buckling shapes. But right now, we'll just look at the conceptual buckling. In this case, loading is applied uniformly. So there's a uniformly distributed stress. And upon this kind of loading, of course, the arch can buckle. In this case, it's actually easier for me to describe the buckling shape. So how does the buckling shape look like? After buckling, the the arch will look like this. This is the buckling shape after buckling. What about the low deflection curve? The low deflection curve look like this. And again, upon loading is going to increase to some point until it reaches the critical load, PCR, like this. Now, once you arrive this critical load, it will go down. Once the buckle takes place, it will go down like this. And then you'll become positive because now it will require the structure to actually apply negative force to continue loading it. And then it will come back to be like this. So if it's hard for you to imagine that why the force is going to be negative, just think about that when the buckling occurs, the arch can actually go into the lower side. And that means from one point, we call this point A, and this point B, and back to this point C. From point A to point B, there's a change of the shape. From point P to point C, there's also another change of the shape. And that's what happens with the buckling of arches. Okay, and okay, I think that we can start. We can go back to the note and to look at the examples I'd like to talk about. Wow, I think that these parts we can talk about later on. A straight column, I'll talk about this. Snapping of an eloping arch, I'll talk about it. Okay, so let's talk about different approaches. Now, this slide shows you the overall. You may call it the overall syllabus of structural stability. And essentially, there are three different approaches that we can use. I'm not counting the computer simulations in this overview. But what you're looking at here is the first approach is what we call the force approach. Well, what's a force approach? Force approach is basically by taking force equilibrium, which perhaps is the most popular approach among students because that's what you learned so far. You have learned how to take force equilibrium from static, from dynamics, from strength of material, from structural analysis, right? That's what you have been doing. And for the force approach, another method is what we call eigenvalue analysis. I will also talk about it in this structural stability. And that's also one way we can use it to determine the stability of a structure. The second approach is what we call energy approach. And energy approach is also what we call the convergence approach because we are going to use the energy methods. And the energy methods are based on either the principle of virtual work or Hamilton's principle. In this method, if you still remember what you learned from dynamics, you remember that when the structure is in motion, there's kinetic energy, right? And there's also potential energy instead of just strain energy. From statics, we learned that when the structure deforms, there's only strain energy. But when the deformation is associated with the velocity, then you can calculate all different kinds of energies, kinetic energy, and even what we call the non-conservative energy. For example, the deflection due to frictional force. But in energy approach, we will calculate these different terms. We calculate the elastic strain energy, internal work, external work, and potential energy, and try to put them together. Force approach and energy approach can both determine the critical load, but only the energy approach can be used to determine the post-buckling behavior, which is why I will talk about energy approach, but in most of the examples I will solve in structural stability, you will see me extensively using force approach because that is the most familiar approach that known to most of students in our department. The third approach is the dynamic approach, and that will lead to the analysis of dynamic stability of any structural elements. Unfortunately, we do not have the time to cover this topic, and this could be the topic for advanced structural stability, which may turn out to be a good news for some students, because that means we will only look at the static problems. We will not look at the dynamic problems. Most buckling failures in real structures all start with a static buckling. So that doesn't put you out of the game. You need to know how to analyze the buckling potential for static structures first, before you analyze the dynamic buckling. Okay, and let's come back to the note so I can start. I think the next one is going to be examples, right? So that's going to be example 1. Let me come back to the notes. From this lecture, I hope you are familiar with my teaching style. And mostly I will be solving problems, not just reading slides. And if we look at the fourth approach, I will give you the conceptual criterion. And these are the criteria we use in our problem solving. So that's the big picture. You may want to take it down for your own understanding. In fourth approach, the buckling criterion is usually this. We want to know that if the deflection, what will be the force when the deflection approaches to infinity? So this is the condition. When delta approaches to infinity. You should note from high school and also from college calculus, infinity is not a number, so you can never say something equals to infinity. In fourth approach, we use that to calculate the buckling load. But in eigenvalue, or this is the actually force analysis, and that's actually another criteria. In eigenvalue analysis, we are not using deflection as a criterion, we are using stiffness. In this case, there are two different kinds of stiffness. The first one is what we call stiffness coefficient. That's what you learn by looking at a structure or looking at a member. In that case, when stiffness becomes 0, that is the condition when buckling occurs. Another example, or is another situation is, what if I don't have a member? What if I have a multi-degree of freedom system? From structural analysis, you know it very well that structural engineers deal with not only just single members, sometimes we deal with trusses, right? In that case, you don't have just a stiffness coefficient, you have a stiffness matrix. And in that case, we call the determinant of a stiffness matrix. And stiffness matrix is defined by capital K. And I have 2 bars, that means it's a matrix. The determinant of a stiffness matrix, when it becomes 0, that's the case we call it buckling. So these are the 3 most important criteria we will use in structural stability. We will use them to find out what are the corresponding buckling force. So let's start with the first example. The first example is here. And